Hi guys, I'm going to go through the answers to question 26.7 with you. This is of radioactive isotopes. The wordy ones you can do yourself, all the answers are on the page, but I'll just go through the mathematical ones. Question 1b is the first maths one, and it says that you have a mass of a sample of wood is 0.50 grams, and it's found to have an activity of 0.11 becquerels. And it says that a living sample has an activity of 0.13 becquerels, so that would be A0. And it says that the half-life is 5,570 years. And it would like you to find out the age of the sample of wood. So we're going to use A equals A0 e to the minus lambda t. We would want to find t, so I'm going to take A0 to the other side to leave this. Take natural log of both sides to get rid of the e. Okay. And then rearrange for t. The problem is I haven't got lambda. Now, so what I'm going to use is lambda equals natural log 2 over t half. But because lambda, my answer I want in years and my half-life's given in years, I can leave lambda in per year rather than per second. So I'm going to use natural log 2 over 5,570, which gives me 1.244429409 times 10 to the minus 4 per year. I'm going to substitute that back into here. So I'm going to have natural log 0.11 over 0.13 all over minus 1.244429409 times 10 to the minus 4. And that'll give me my time in years. And when you do that calculation, you should get 1342 years, which is 1,300 years to two significant figures. And that's how you do question 1b. I'm going to now look at question 1c. Sorry, I'm going to now look at question 2. So question 2 says you have a radioactive isotope of 131 iodine, and it's used for medical diagnosis, and it has a half-life of 8 days, and it has to be given to a patient a glass of water. The passage of the isotope through each kidney is monitored. The isotope required to have an activity of 800 times 10 to the 3, so 800 kilobecquerels at the time it's given to the patient. So what the question then asks us to do is work out the activity of the sample 24 hours after the sample was given to the patient. So we're going to use A equals A0 e to the minus lambda t. Now, because we want activity in becquerels, we're going to need to convert all of these into seconds. Okay, but we also don't know lambda, so we need lambda in per second. So to find lambda, I'm going to do natural log 2 over t half, but I need to convert my 8 days into seconds. So 8 days, and there's 24 hours in a day, 60 minutes in an hour, and 60 seconds in a minute. So that would be our calculation. And lambda comes out as 1.0028171102 times 10 to the minus 6 per second. Then need to substitute that into here. So my A0 is 800. My lambda is minus 1.0028171102 times 10 to the minus 6. And my time is 24 hours, but I need that in seconds. So 24 hours, 60 minutes in an hour, 60 seconds in a minute. If if you do all of that, you should get 733,603, which is 734 kilobecquerels. Part 2 then asks, well, 24 hours before that, what was the activity of the sample? Now, because the sample has reduced by this much, the difference between 800 and 734 in 24 hours, 24 hours before this, okay, it would have, over the 24 hours before this, it would have decreased the same amount. So if we work out the difference between these two, so a change in time of 24 hours gives you a change in activity of 800 minus 734, which is 66,000 becquerels. So 24 hours before this, this would be 66,000 becquerels higher. So I'm going to call it A0, the one it's talking about 24 hours before A0 would be 866,000 becquerels. Then the hardest part of the question, it wants you to figure out how many, the mass of the sample that's given to the patient. So it says, no, it's part B. The reading from the detector, no it doesn't, sorry, part 3. The mass of the 131 iodine in the sample when it was given to the patient. So to figure out the mass of the sample, we're going to need to know how many atoms are in there, or how many nuclei. So we're going to use A equals lambda n. Okay, and what this allows us to find n, so that's going to be A over lambda. When it was given to the patient, A was 800 kilobecquerels, so 800 times 10 to the 3. And lambda's given here, okay? Minus 6. When you carry out that calculation, you find out you get 8.63567,243 times 10 to the 11 nuclei. So to find out how much that weighs, we need to then figure out how if we use Avogadro's number, so Avogadro's number is 1 mole. Okay, so we want to figure out how much, what fraction of Avogadro's number we have here, and that will give us the number of moles. So the number of molecules we've got is this, which we've just figured out. And if we divide that by Avogadro's number, which is 6.02 times 10 to the 23, that will give us the number of moles. And then the number of moles, I've not done it, so let me just do that calculation. That gives me 1.434497081 times 10 to the minus 12 moles. Okay, now we know that 1 mole will have a mass of 131 grams, or 0.131 kilograms, and we know we've got this number of moles. So if I multiply these two numbers together, it should get the mass. And that answer should be 6.8 times 10 to the... hang on, I can't remember what you get. Let's do it. 0.131 times 1.43447. Sorry, 97081 times 10 to the minus 12. And we get 1.879191176 times 10 to the minus 13, which equals 1.9 times 10 to the minus 13 kilograms. Now just check that's right. Yes, it's right. Okay, so there's your answer for that one. Last one. Question 4, talking about a cardiac pacemaker. Well, question 3 hasn't got any numerical work in it, so you can just have a look at the page to find the answers to those. Question 4's got a bit of numerical work, so we're going to look at part B. And it tells you that you've got strontium-90 isotope is used as a power source for a weather station, and it tells you it has a half-life of 28 years, and it emits beta particles, and the beta particles have an energy of 0.40 mega electron volts, and it also tells you earlier that 1 mega electron volt equals 1.6 times 10 to the minus 13 joules. And it also tells you you have a mass of 10 grams. And it would like to know its activity. So in order to calculate its activity, we're going to need to use the equation A equals lambda n, but I neither know lambda or n. So I'm going to find lambda first. So lambda is natural log 2 over t half. So that's going to be 28 years, 365 days in a year, 24 hours in a day, 60 minutes in an hour, 60 seconds in a minute. And that gives me lambda as 7.8498403325 times 10 to the minus 10. To find n, I'm going to need to use the fact that 90 grams of SR will be 1 mole and have one, it will have 1 Avogadro's number of nuclei in it. So if 90 grams is equal to 1 mole, okay, we've got 10 grams. Okay, so the number of moles we've got, n, is m over mr, so we've got 10 over 90, which gives us 1 over 9. Okay. We then want to find the number of molecules, that's n equals na. So I've got 1 over 9 times Avogadro's number, which I believe gives me an n of 6.68888889 times 10 to the 22 nuclei. If I then substitute these two values into A equals lambda n, I should just multiply them together. I'm not going to write them out again, but if you multiply them together you should get 5.256670973 times 10 to the 13, which equals 5.3 times 10 to the 13 becquerels, to two significant figures. And what part B then says is calculate the energy released per second. For part B2, energy per second is power. So we're trying to find the power of this source. Now, we know the energy of one of these is 0.4, one of these betas, mega electron volts, okay? And we need something per time, but we know activity is how many given per activity is the number per second. So if we multiply that by the activity, which we've just figured out, that would give us the power in mega electron volts per second, but the question wants it in joules. So in order to do that, you're just going to use the fact that 1 mega electron volt is 1.6 times 10 to the minus 13 joules. So the total power is going to be 0.40 mega electron volts times this 1.6 times 10 to the minus 13 times 5.256670973 times 10 to the 13. And that'll give me the power in joules per second. And if you calculate it, you end up with about 3.4 joules per second. So from that you can figure out if you're getting enough energy per second and if your remote weather station is powerful enough. Okay, thank you very much. If you want any help with any of the wordy ones, let me know and I'll go through them with you. Okay, bye.